Okay, so this is okay. We will continue chapter 14 on the topic of wave and sound. Okay, wave and sound. So let me share the slide first. Okay, I think last time, okay, we already covered. Okay, let me do some recap on what we have learned. Okay, so this is the topic of wave and sound, chapter 14. All right, so in this topic, we will learn about type of wave. Okay, I think we have already covered because the type of wave will consist of a longitudinal wave and also a transverse wave. Okay, transverse wave and longitudinal wave. And how about wave on a string? So wave on a string. So you will know some things that related to wave, but occurs in on a string. Okay, so in this case, they will talk about v that equivalent to the square root of f over mu. Okay, v equals to square root of f over mu, which mu is based on m over l, mass per unit length. Okay, and now we go to sound wave. Okay, the sound wave, and also we try to finish everything about sound that's considered related to intensity, sound intensity. Okay, we will learn some things that related to Doppler effects, the superposition and the interference, and together, and lastly the standing wave. Okay, so this one we already covered the transverse wave, okay, the definitions of transverse wave, the definitions of longitudinal wave, right? Okay. Uh, so okay, the wavelength, okay, the frequency and the speed, okay. How can we define wavelength, frequency? Wavelength, if lambda is lambda, a frequency is f, and the speed is v. So v equals to f lambda. Okay, like I'm saying, this is wave on the string. Okay, we talk about the speed of wave on the string, which contribute by v equals to f over mu, which mu is a mass per unit length. Okay, and v is of course a meter per second. Okay, we already did the some questions. Okay, and also the reflections. Okay, the reflections at the fixed end and also at the loose end. Okay, and the sound wave. Okay, so we'll talk a lot about sound wave. The applications of sound wave will come afterwards. Okay, the sound wave are longitudinal wave that's similar to the sound of a wave on a silky spring. Okay, and we also talk about the speed of sound. Okay, there's the difference between the speed of sound for some material. Okay, for example, a solid, we have liquid and we have gas. Okay, that we will have a different speed of sound on the different materials. Okay, so so we also talk about loudness, which related to intensity, and the pitch is related to frequency. Okay, pitch and loudness. Okay, so for examples, in this case, okay, we can say that if you look at the examples of this is bad. Okay, bad. Okay, kelawar, and also we have whale. Okay, ikan paus. So they also have their own frequency, their own mediums of the sound. Okay, if bat is talking to each other, so bat is maybe communicating with other bats, or maybe they are navigating, flying inside the cave, okay, a very dark cave. So how can they survive? Okay, so they are using a frequency, with frequency that a human cannot hear because it falls under ultrasonic. Okay, so human being also will be only on the sonic part. Okay, which contribute from the 10 power of 1 and the 10 power of 4, from 20 hertz into 20,000 hertz. That is called sonic. And afterwards, okay, the bat is on the ultrasonic, okay, while whale is in the infrasonic, okay. So we cannot hear uh, what the what types of uh, I mean communications that they are having, so we cannot easily understood, okay, because of the difference in the frequency. Of course, you cannot understand how the animals talking to each other, right? So when we talk about sound intensity, okay, so of course it is related to loudness. Okay, the loudness of sound. Okay, kekuatan bunyi. Loudness of sound is determined by its intensity. Okay, what is intensity? Intensity is the power per unit area. Okay, power per unit area. That's why the unit for the intensity is watt per meter square. Right, watt per meter square is due to watt is for power, while A is the surface area. A is the area which it will contribute by meter square. Right. So for the vocal cord, that for the all normally we can say from the point source. Okay. So point source means that from our vocal cord. Okay, point source it's like a very guli macam tu. Okay, just small as guli. So we are saying that, okay, the surface area of the sphere, okay, the point source is actually 4 pi r squared. So normally we will use 4 pi r squared as our surface area for a point source. Okay, but in the case of maybe we have our own area like this one, okay, a rectangular, so we can say the area is rectangle. Okay, so it's easy, right? So don't care much or don't bother much about the area, because you need to define which area. Okay, if the area is the triangle, okay, the question will explain to you. If the area is triangle, then okay, you must use a triangle. How to find area for the triangle. Okay, so don't bother much about the area because it will keep changing. But for a point source, it is a 4 pi r squared. Okay, so this is the examples of the intensity. So two people relaxing on a deck listen to a songbird sing. Okay, this is a songbird sing, right? One person only 1 meter, so this one is only 1 meters. Okay, the distance between the birds and the first person is 1 meter, and here's the sound with an intensity of 2.8. Okay, the first person will hear 2.8 10 power of -6 watt per meter square. What intensity is heard by the second person, who is 4.25? So this is 4.25 meters, is slightly behind the person number one. So what can the person number two hear the intensity? Okay, so we need to define, we need to do using the equations of I squared 2 I2 equals to R1 over R2. This one is the is actually the derived equations. Okay, the derived equations from the I. I is P over A. But this is for intensity one. Okay, P over area one. Okay, power one and area one. Okay, or power, we can say power is the same, so area one and that, and also of course a power. Okay, because we are using the same power. Okay, the same sound means the same power. Okay, so for I2 we'll have P over A2, and now we can say, okay, we'll try to bring P and P together, so we are saying that, okay, I2 R 2 square is equivalent to I1 R1 square. Okay, and that is due to because of when we talk about area, this should be 4 pi r squared. But when I1 have 4 pi r squared, I2 also have 4 pi r squared. We can cancel out 4 pi. Okay, this is R1 R2. This is R1, R2. Okay, for pi and for pi will cancel out each other, and only will be left I1 R1 square equivalent to I2 R2 square. Okay, and because of that, okay, so we can use these equations to find the second intensity. So you need to do on your own. Okay, please try it out. Okay, get your calculators. Okay, try it out together with me. Okay, try to punch in your calculator in order to get this value. If you can get this value, then it should be okay. Right? All right, so while trying, so let's look at number B. What is the power output of the bird song? Okay, power output, as I'm saying, the power output should be equivalent. It should be equals because the power, the sound comes from one bird. Okay, comes from the original, meaning that comes only the source of the sound is only one, meaning that the bird will only produce one sound. Okay, but the intensity heard by different person, okay, because of the distance, okay, different distance will hear a different intensity. Okay, because intensity, if you look at the equation, R equals to P over A, so intensity directly will be influenced by uh, P and A. Okay, if the power is increased, then intensity also increase. So when we hear the loudness of the sound, so we know that the intensity is increasing. But for if area is decreased, if area decrease, so we know in that area we have a distance. Okay, R. We have a distance. So if the distance decrease, so the intensity will increase. That is how the inversely proportional. Because I and A is inversely proportional, so we need to understand that I and A is inversely proportional. If A is increased, then I should be decreased. And if A is decreased, and I will be increased. So in this case, we already have I2 and I1 is P over A1. So we can have P equals to I1 plus A1. So we have equation 3.52 10 power of negative 5 watt. Okay, look at the unit. We are using watt. Why? Because we want to know power. Okay, so please look at the unit used in the equations, watt over meter square. Okay, watt and of course meter square, right? And if we try to calculate for I2, for P at I2, so we will also getting same answers. Okay, same answer, which is 3.52 10 power of negative 5 watts. Look at how they solve the problem. Okay, look at how they write down the equations. Okay, you should do like this. Well, when you do a final part in your final examination, make sure you obtain the value, you obtain the equations first, and then you substitute the value, and then the final answer with the correct unit. So you need to do like this. Okay, then you will have a very I mean uh, your answer should be clear enough for the examiners to to mark your final. Okay, right. So now we look at the back. Can use this decrease in sound intensity to locate small objects in dark. Like I'm saying, that's how they are navigating, they communicating inside the dark cave. Okay, so of course, when we look at the intensity of the sound, okay, so okay, look at the left part of the table, saying source of the sound. Okay, from the jet plane at 30 meters and at the threshold of hearing. Okay, in sound intensity, in sound, okay, they will have um, two types of unit. Okay, we are saying intensity will have two types of unit. Okay, number one is sound intensity. Okay, the one that we did earlier is the sound intensity. Okay, which means P over A, or P over 4 pi R squared. So that is sound intensity. Another sound unit for the intensity is called sound level. Okay, sound level. Okay, the unit for sound level is dB. What is dB? Decibel. Okay, DECIBEL. Decibel. Okay, and you can look at the values. Okay, look at how they present the values. Okay, from the jet plane. Jet plane is very high, very intense sound. Okay, jet plane at 30 meters. 30 meters is like maybe just slightly bigger than bangunan pentadbiran. Okay, a threshold of pain, a loud rock concert, a siren at 30 meters. Okay, truck traffic. Okay, busy street traffic. Okay, maybe a quiet radio whisper. That all okay will have a different sound level and also sound intensity. Okay, so please differentiate between sound level and the intensity of the sound by looking at the units. Okay, the unit for sound level, or sometimes we call it as intensity level. Okay, some books will call intensity level, while for the sound intensity is watt per meter square. The intensity level, sound intensity level, is called decibel. Okay, we will have we can convert easily time intensity to sound intensity level. Okay, so one thing you should know when we talk about threshold of hearing. Okay, this one, look at the value. Okay, this is threshold of hearing, meaning that the least that human can hear sound, the least, paling sikit, okay, is 0 decibel, almost cannot hear anything, but this is the limit. Okay, the lower limit for the human being to hear the sound. This is called threshold of hearing. Look at the decibel, 0, but the intensity level is 1 times 10 power of negative 12. Okay, this is almost always um, always be tested in the past year's final examinations. Okay, so at least you have to know what is the threshold of hearing. They are not questioning you about what is the value of threshold of hearing. No, what is the intensity value of the threshold of hearing? Okay, they will use a threshold of hearing, okay, to find the intensity level. Okay, so afterward I'll show you. So this is it. When you listen to a variety of sound, a sound that seems twice as loud as another is 10 times more intense. 10 times more intense, therefore we use a logarithmic scale to define the intensity values. Okay, so this is decibel. Okay, the definitions of the intensity level beta. Okay, beta. Look at how they use beta. Okay, yeah, normally please look at this uh, parameters terms used for the each term, because sometimes you will get confused between A, okay, like A and alpha. Okay, this is not the same thing. Okay, alpha is not A. Okay, so please remember, this is not the same. This is not B. This is beta. Okay, beta is 10 log I over I naught. Okay, 10 log I over I naught. Log is the base log, meaning that log 10 I over I naught, which I naught is what? I naught is the threshold of hearing, while I is the intensity at that particular value. Okay, so I naught is the threshold of hearing. So for decibel, I naught is 0. Okay, so in these equations, I is your intensity, I naught is the intensity level, sorry, the threshold of hearing, which means I is 1 times 10 power of negative 12 watt per meter square. So we should put this value in at I naught, and then we should calculate the beta. When we want to convert from intensity to the intensity level. Yeah, remember, I is intensity, okay, and beta is the intensity level. Okay, so please differentiate between intensity level and intensity. So there are two different terms, which one is intensity level and another one is intensity. Okay, so these are the different decibels. Okay, maybe eardrums, jet taking off, pain. Okay, this is called threshold of hearing, 0. Okay, at pain, this one is what we call as threshold of pain. Okay, loud, loud rock band, thunder, subway, heavy traffics. Okay, so they are all have values for the intensity level. Yeah, the decibel is for intensity level. It is not an intensity because intensity, the unit is watt per meter square, while the intensity level is decibel. Okay. All right. So let's look at the examples. Okay. A crying child emits sound with an intensity 8 times 10 power of negative 6 watt per meter square. Find A, the intensity level in decibels for the child sound. Okay. Find A because this one is considered as I. Find A, the intensity level in decibel. Okay, the intensity level in decibels, so meaning that you want to find what is better for the child sound. Okay, child sound in part A only. Okay, for the child sound. And B, the intensity level for this child and its twin. Okay, so this is for part B. Okay, this one is for part B, this one is part A. Okay, both crying with identical intensities. Okay, so look at what they did. So they need to establish the equation first. So this is equation. Okay, beta is equals to 10 log I over I naught. Okay, you know that I naught should be threshold of hearing. What is threshold of hearing? 10 power of negative 12. Okay, and the intensity at 8 times 10 power of negative 6. Okay, so now we convert it to this one. Okay, negative 12 bring to the upper to the to bring to the numerator part. So 10 power of negative 6 plus with 12, because negative, when it goes to the numerator part, now it become 10 power of 6. Okay, so now okay, we need to use a little bit of uh, 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 logarithm uh, equations. Okay, meaning that in this part, okay, when times, so it should split up into plus, okay, to the addition. So 10 log 8 plus, okay, plus 10 log 10 over 6. And then afterward, you just punch your calculator to get 69 decibel. Okay, you remember, okay, we will use a little bit informations in the logarithm chapters, okay, maybe in your secondary school. So try to remember back, okay, and then you will get 69 decibel for one child that emit a sound of intensity 8 times 10 power of negative 6. Okay, so on part B, so there are two identical twin. Of course, the twin is identical, that will have a double intensity, meaning that intensity for baby blue and of course the baby orange is the same. Okay, so you need to double up this one. Okay, double the value of intensity. Okay, again, so on this part, okay, try to differentiate, try to, okay, now use some little bit of informations of logarithm, key index and logarithm. So in that case, you will getting 672 decibel, slightly higher than just one baby. So two baby, definitely decibel will increase. Okay, look at the value from 69 become 72, where we have two identical babies, two identical intensity. The value of the decibel also increase. Remember, what is beta? Beta is intensity level. Okay, beta is intensity level. Okay, right? So we may break for 1 minute, and then we will continue to the Doppler effects. If you do have a problem, please start your problems uh, on the chat box. Thank you. Okay, now let's continue. Okay, so this is the Doppler effects. Okay, for those still remembering when our nations been hit by the news of the loss of MH370. Okay, so always talk about the Doppler. Okay, they are using Doppler to locate some ping sound, um, ping locations where the flight is actually uh, trying to avoid, okay, or trying to go when they are out of the radar. So we can easily detect the sounds from the aircraft, so using a Doppler effect. So what is the Doppler effect? So one of the most common physical phenomena involving sound is the change. Okay, the words is change in pitch of car horn as the vehicle move past us. Okay, so remember, let's say if you look at the picture, you look at the figures, okay, you can see that there are some source of the sound, and of course you can see the persons who are playing the skateboard, okay, who are on the skateboard is actually observer, okay, meaning that this person will hear the sound. The question now is the sound, okay, when the observer, okay, try to be near to the sound, okay, this he easily can hear that the sound is actually increasing louder and louder and louder, okay, and when it pass through the sound, okay, meaning that go away, okay, go away, move away from the sound or move away from the source, then the sound is actually getting dim. Okay, the sound is actually decrease and decrease, and finally it will disappear. Okay, when observer moves toward the sound, the wave appears to be higher. Okay, and the frequency appears to be higher as well. Okay, so this Doppler effect we'll talk about. Okay, when you observe. Okay, when you are right now observer. So so that is another one thing. Okay, where you have a stationary source, and what if the source of the sound is like a moving ambulance? Okay, you will hear ambulance from far away because of the sound. Okay, you know that the ambulance is keep coming, is getting nearer to you. Why? Because the sound is getting louder. So that's how you know that, okay, if you are in the middle of, if you are in the pathway of the ambulance, so this time you should be avoid the pathway of the ambulance, because you know that the ambulance is getting nearer to you. Okay, so this is all due to the Doppler effect. So that's how you can adjust, or you can see. So this is the moving observer. Okay, the moving observer. So what is the moving observer? Meaning that sound. So this is the source. Okay, stationary source. So meaning that the source doesn't move and the observer move. Okay, the observer move near and away. Okay, this observer will comes towards the source and afterward it's moving away. Okay, what will happen if the observer getting nearer to the stationary source? Okay, the idea of the idea of the Doppler is this person, okay, will hear a frequency. Okay, will hear a frequency, meaning that the frequency of will keep changing as the place changing. Okay, and far away maybe the frequency is low. Okay, because the frequency is low, but while getting nearer to the sound, the frequency will be increased. So that's why for the observer's frequency, okay, they put prime, f prime. Why f prime? Because f prime keep changing. Okay, keep changing. It doesn't stay at one values only, right? So it keep changing because the observer will hear, for the stationary source, the observer will hear a different frequency as it move towards the sound. Okay, maybe at the far, okay, he will hear, let's say, 100 hertz. But getting nearer to the sound, he will definitely hear an increase of the frequency, maybe 150 hertz. And afterwards, when it go away from the sound, okay, maybe he will only hear 80 hertz. So you know, from 100 to 150 to 80, there are some change in frequency. So that's why the frequency of f prime is not a real frequency. The real frequency is coming from the stationary source. Okay, the sound will produce the original frequency, but the f prime is what is due to the frequency heard by observer. Okay, frequency heard by observer. So that's why you need to understand that the Doppler is actually a reference, a point of reference, the frequency heard by the people who are not in the same reference point. Okay, maybe some of you will hear, maybe if you are you have three different person. So person number one, okay, number two here, and number three here, definitely will hear a different frequency. If you ask them, okay, they will hear, okay, maybe this one will hear kuat, perlahan. Yang ni sangat kuat dekat tengah-tengah, sangat kuat dekat hujung, perlahan lah dia bunyi dia. That is due to the distance. But that's why in this topic we will discuss in terms of moving observer, and afterwards moving object, moving source, and Lastly, the third cases is the moving observer and moving source. Okay, if the observer were moving away from the source, only the signs of the observer speed would change. Okay, the signs of the observer speed will change. So in this case, to summarize the Doppler effect for moving observer, we are saying that f prime, okay, f prime is equivalent to 1 plus minus u over v. U is what? U is the frequency of the velocity of observer. V is speed of sound times f. F is what? Original sound, original frequency. And this one is 1. Okay. So for the moving towards the observer, moving towards the sound, we will use plus. Okay, we will use plus. This is moving towards sound. And this one is for moving away. Okay, meaning that, okay, just to summarize, to really summarize this thing is the frequency, this one. Okay, let's say if you do have 300 hertz. So for the moving towards the sound, okay, when you calculate, you must get, okay, moving towards, you must get value higher than 300 hertz. Definitely, the value should be higher than 300 hertz if the f is 300 lah. Okay, but if moving away, it should be less than 300 hertz. Why? Because it should be moving away. Okay, is getting far. It's getting far. The distance is increased, and of course, it will affect the frequency of the observer. Remember, f prime is the frequency of the observer. U and V are positive quantities. The minus sign is used when the observer moves away from the source, and the plus sign is used when the observer moves towards the sound, the source. Okay, and maybe, okay, sometimes they will use like this. Maybe you will encounter F O. Okay, some books will use F prime. Maybe F O. F O means observe frequency of the observer. V plus minus V naught over V. Okay, times F. Same thing. Okay, V plus minus V naught over V. So V meaning that this one is the speed of sound. Okay, and V naught is the observer speed, because this is a moving observer. Okay, V plus minus V naught over V times F. Also, okay, this is for observer's frequency. So this is actually the same equation. Okay, in my slides we'll use F prime, but in your textbook, okay, definitely they will use FO, or observer's frequency. Okay, all right. So this is the moving observer. A street musician sounds the A string of his violin, producing a tone of 440 Hz. So this is what? This is F. What frequency does a bicyclist hear as he approach? He approach meaning that moving towards. Okay, and recedes from the musician with a speed of 11 meters per second. So, okay, try to use the equation. So F equals to F V plus minus, okay, VO over observer speed, V, okay, meaning that 440 times with 343. Okay, I forgot to tell you the speed of sound in air. Okay, because the medium here is air is 343 meter per second. Okay, 343 meter per second. So I know that this is 343. Moving towards is plus. V naught is 11 divided with 343. Now you will have a certain value. Okay, so it's quite simple using. So if moving away, then moving away should be FO equivalent to AF V minus V naught over V. Moving away, so 440, 343 minus with 11 divided by 340. So you will have the value of 426 Hertz. Okay, this one you will have 454 Hertz. Okay, they are using my slide. Okay, like my slide, so they are using this kind of equation. This equation is actually the same as the equation. This one is from your survey textbook. So I'm encouraging you to use this equation. Okay, use this equation instead of my equations. Okay, because you will see in your textbook you will see F naught equals to F plus V minus V naught over V. Okay, so this is the moving source, right? Moving source. So again, the one thing you should know about moving source is the source is moving while the observer is stationary, meaning that our observer doesn't move. Okay, but the concept is still there. Okay, the sound is getting nearer to the observer. So can you predict? Okay, can you predict the observer's view in terms of the moving source that's going towards him or towards her? So of course, in this type of situations, okay, the observer's frequency will definitely increase. Okay, observer will hear when the source is moving towards her or him. So definitely she or he will hear an increase in frequency. He will hear louder sound. Okay, and if the source is moving away, and of course the frequency will be decreased. Okay, so we can define that the Doppler effects for moving source is actually F prime 1 over 1 minus plus U over V. Okay, 1 over 1. So when we talk about FO, so FO equals to F V over V minus plus Vs source. Okay, it's like that. Okay, look at this value. It should be minus, minus plus. Okay, minus plus. Right? So this is only for moving source. Right? So this V is 343. This one V is 343. Okay, this one still speed of sound in air. This one is speed of speed of sound. Speed of sound source. Speed of source. This one is the original frequency. And this one is the observer's frequency. Okay, so you should know the situation. When the sound is getting near to the observer will hear louder, or the frequency of the observer should be increased than the original. It should be greater than the original frequency. But when the sound is moving away from the observer, then the observer will the observer's frequency will be decreased compared to original frequency. So we can look here. A train sounds its whistle as it approaches a tunnel in a cliff. Okay, the whistle produces a tone of 650 hertz. Okay, the whistle produce, meaning that a train sound its whistle as it approaches a tunnel. So, a train produce whistle. So, a tone of this one should be F, and the train travel with speed 21.2. So this is, should be Vs. Find the frequency heard by an observer, part A. Find the frequency heard by the observer standing near the tunnel entrance. Okay, so this should be moving away. So this should be FO. Part B is the sound from the whistle reflects from the cliff back to the engineer. Then what frequency does the engineer hear? Okay, we do it one by one. Okay, so first is moving towards. Okay, moving towards, meaning that come from 650 hertz. This is the original one. So please use the equation from the survey textbook. V over V minus plus Vs. Okay, why I'm using Vs? Because this is the speed of source. Okay, the speed of source. So the speed of source is 21.2. The sheet one should be 650, 343, 343. Because it's moving towards, it should be negative. Vs is 21.2. So this one you will get 693 hertz. It's increased, but it's slightly greater than 650. Okay, what happened on part B? The sound from the whistle reflects at the cliff. Okay, so this happened when you are approaching the cliff. So you will hear the cliff is reflected down because of the echo. Okay, reflects from the cliff back to the engineer in the train. So maybe there's some engineer. Okay, so what frequency does the engineer hear? Right, so right now the frequency you are giving to the observer is 693. Okay, so from 693, so this should be the original before we do the number B. Okay, so this should be 9693. 693 should be the original frequency, and right now we have a moving observer. Okay, moving observer towards him. So we need to do FO equals to F V plus VO over V. So again, 693. Not you are not using 650 because right now the frequency delivered by the sound is essentially 693. Okay, 693. So we need to start with the 693 frequency times 343 plus with 21.2, and of course V. Okay, 21.2, and of course V is 343. Okay, so you will see there's some increase, and then because of this approaching 736 hertz. Okay, 736 hertz. So it's actually getting nearer, and of course the frequency is getting greater. Okay, I have one question here. Can we write the frequency in decimal point? Definitely yes. Okay, boleh ya, boleh. So moving observer and a moving source. Okay, how to do this one, right? So to simplify the moving observer and moving source, okay, so we can use the equation of this. FO equals to F, okay, V plus minus VO over V minus plus VS. Simple. Okay, don't look at this one. This one is quite complicated. Just use this one. Okay, but you need to define if the situations is getting, you must use the right sign. Okay, the right sign, maybe positive or negative, to define the velocity. Because you need to know that the V is always speed of sound in air. So the value is 343, always 343. Now the difference is when you have V naught, okay, the speed of observer, and this one is speed of source, and this one is frequency. This one is observers. Okay, so you need to define positive and negative of the uh, observers signs, right? Because it should be different. Okay, so you can look at your textbook, or maybe we can discuss later in the tutorial. Okay, and how uh, to solve the problem of moving observer and moving source. But at this point, you should know, okay, to use the equations. Okay, to use the equation, please. Okay, I'm encouraging you not to use my equation, my slides. Yeah, my own slides equations, but to use the survey books equation. Okay, what is the survey books equation? Here. Okay, FO equals to F times with V plus minus VO over V minus plus, okay, VS. That's all. Quite simpler. Okay. So please use this equation. Please use this equation, okay? All right. So whenever you need to use, okay, maybe for moving observer, so I think the stationary observer, then VO should be 0. Okay, for the stationary source, then VS should be 0, right? And this one is for moving towards the sound. Moving towards the sound will use V plus or V minus. But moving away, they will definitely use yang bawah. But, okay, please look at the sign. Okay, anything else, okay, the basic is still there. The sound, when the sound is getting near to the observer, okay, the frequency increase. When the sound move away from the observer, the frequency decrease. The frequency what? The observer's frequency. Heard by the observers. Okay? The sound doesn't change the frequency. Frequency dia sama saja. Yang berubah ialah frekuensi yang didengar oleh observer. So you must understand that thing. Okay, frequency heard by the observer will keep changing as the points of reference. Okay, so in the numerator, the plus sign corresponds to the case in which the observers move in the directions of the source, whereas the negative sign indicates motion in the opposite direction. In the denominator, the negative sign corresponds to the case in which the source move in the directions of the observer, whereas the positive indicates motion in the opposite directions. Okay. Alright, so the Doppler effect has many practical applications, such as radar, speed radar, medical diagnostic, and of course astronomical measurements. So that should be the end of the Doppler effects. So far, so good. Okay, so we will break for 1 minute. Okay, and we will continue. If you do have a question, then please put in the chat box. Okay, so let's continue on the superposition and the interference. Okay, so the concepts of superpositions and interference, of course, will relate to the wave. Okay, right now we are studying wave. So the combinations of two, okay, combinations of two or more waves to form a resultant wave is called superposition. Okay, the combinations and how a wave combine, so we will see. So that is what we call as superposition. Okay, so let's say if you do have a wave on y as y1 and wave on y2. Okay, so the resultants of y plus y1 plus y2 will be like this. Okay, this is the resultant. The third part will be the resultant. Right. If two pulses combine to give a larger pulse, this is constructive interference. So I think most of you already remember during your school days, we learned about interference. Okay, the interference. So we have two types of interference. What means the number one is constructive interference, and of course, the destructive interference. Okay, so what is constructive interference and destructive interference? So we look at. So let's say if you do have one crest, okay, going to the right, to the right, and one crest going to your left. So it will meet at some point to become this. Okay, this is what we call constructive. However, okay, in order to get the constructive, there's some rules to follow, maybe some conditions to follow, like same amplitude, same phase. Okay, you need to define phase. Okay, maybe some amplitude and frequency. So these are we are saying about coherent. Okay, coherent source. Okay, maybe later you will learn about coherent source, but this should be the conditions on how we are getting constructive interference. Okay, how I'm saying this one is constructive interference. Then look at the wave here. Okay, in the beginning, it's slightly smaller, but okay, smaller. And now, when they meet together, now it become bigger wave. So bigger wave means constructive interference. So look at the part B. So part B. So you see the wave, the crest is not actually in phase. So when they meet, okay, it will decline. So this is called in destructive. Destructive interference. Now it's like a decline. Okay, this kind of destructive interference. And okay, and when they are splitting, so we actually look at, okay, oh, there are two waves that meet that are not in phase. Okay, so two-dimensional wave exhibit interference as well. This is an example of an interference pattern. Okay, examples of the interference pattern. So how can we define constructive and constructive and destructive interference while they are using this kind of a picture? Okay, so don't bother much about constructive on how to draw a pattern of constructive and destructive. As long as you know, when they combine, it becomes bigger, so that will be constructive. Okay. About the drawing, the sketching is not really important right now. Okay, but when you do your PH 1098 in the second semester, so you will learn later. You will learn these things further. Okay, in terms of the topics interference. Okay. So at point A, the distance to each source is the same, hence crest meet crest. Okay, the source, the distance to each source is the same. Okay, so let's say at point A, so when we calculate, so when we measure from point A to source number 1 and point A to source number 2, it will give you 0. Okay, 0 meaning that let's say 10 centimeter and another 10 centimeter. So 10 minus 10 become 0. So 0 is called 0 lambda. Okay, what is lambda? Wavelength. Okay, at point B, okay, at point B, the distance from one source is greater than source 2 by half of wavelength. Hence, crest mid-throw. Thus, destructive interference. So easy to understand, okay? Like this, okay? At point A, okay, crest mid-crest. Crest mid-crest. So, when crest mid-crest, you will have starting from 0, the different, the path length difference, panjang dia, antara source number 1 and source number 2 should be 0, 1, 2, 3, and so on. Meaning that the integer, okay, the integer starting from 0. So 1, 2, it cannot be 1.5, it cannot be 1.2, it should be 1, 2, 3, 4, 5. So that will give you constructive interference. While when you are subtracting the length between source number 1 and source number 2, so let's say point B, okay, this one is 8.5, this one is 11. So 11 minus 8.5, so you will have 2.5 in different, 2.5 lambda. So 2.5 lambda is considered to be destructive interference. So this is how you're doing by look at the difference in the path length. Okay, difference in the path length. So this is called path length difference. It's really good to understand the concepts of constructive and destructive. Okay, so at point C, the distance from source number 1 is greater than source number 2 by 1 wavelength. Okay, so 1 wavelength. Tadi on point A, 0 wavelength. Okay, so 0 is considered constructive. 1 is also considered as constructive. How about 2? Yes, constructive. How about 3? Yes, constructive. How about 0.5? No, it should be destructive. How about 4.5 lambda? Destructive. So easy to understand why you have the different in path length. Okay. Okay. So let's look at the examples. Two speakers separated by a distance 4.3 meters emit sounds of frequency 221 hertz. The speakers are in phase with one another, so meaning that they produce the same phase sound. Okay, two persons listens from a location 2.8 meters directly in front of one of the speakers. Does the person hear constructive or destructive interference? Okay, we cannot know. We need to calculate first. Okay, so in here we have frequency. So I write down this one should be the frequency. This one is the distance. Look at the distance is 4.3, 2.8. Now 4.3 is this one. Okay, 4.3 meters. This one is location directly in front of 2. Okay, this one is 2.8 meters. Okay, so using V equals to F lambda, so we need to find lambda equals to V over F. What is V? Speed of sound in 3, 4, 3 divided by F 2 to 1. So you will get 1.55 hertz. So the lambda is 1.55 hertz. Alright. So in order to get D2, say because we doesn't know what is D2, so we need to do a Pythagoras theorem. Okay, Pythagoras theorem like this. So this is Pythagoras theorem. So in the end, we will get 5.13. D2 as 5.13 meters, and D1 is 2.8. When we subtract 5.13 to 2.8, so we will get 2.33 meters. So does this include? Does this show that this person will hear the constructive or destructive? Okay, does the person hear constructive or destructive? So when we divide D2 minus D1, over lambda. Okay, over lambda. So we should get, the answer should be 1.5. Okay, so 1.5 is considered to be destructive interference. Okay, destructive interference. It's not because the different, when we have path line 0, 1, 2, 3, then there should be the constructive. But if you have 1.5, 2.5, 3.5, so that is the value for destructive. So this person will hear a destructive interference. That's how you determine either it is a constructive or destructive. There are one more examples in terms of the interference. Okay, the speakers shown to the right have opposite phase. Okay, the speakers shown to the right have opposite phase. They are separated by a distance of 5.2 meters and emit sound with the frequency of 104 hertz. Okay, 104. A person stands 3 meters in front of the speakers, okay, and 1.3 meters to the one side of the center line between them. Okay, the one here. If you don't understand the question, then just look at the figures. What type of interference occurs at the person's locations? Okay, so you need to do some calculations using the one that we did earlier, like this. So let's say for lambda, so how to determine the lambda? You need to do V equals to F lambda, lambda equals to V over F. What is V? 343 divided by 104. So you will get 3.3 meters. Right. What is a D1? So you need to calculate D1. Right. So how to calculate D1? So right now you will have 1.3. Okay. This one is 5.2. 5.2 divided by 2. So you will get 2.6. Okay. 2.6 each. 2.6 plus 1.3. So it should be 4.9. Okay, 4.9 times 4.9 square. This one is 4.9. Okay, square this one to get D1. And the same goes to D2. So you minus, you get 1.65. 1.65 divided by lambda, so you get 0.5. While looking at the equation, the value is 0.5. You know the interference occur here, which should be destructive. Why? Because this is a 0.5. Very easy, eh? Very easy. So if you get one integer number, so that will give you constructive. Okay, so I think we should break for one more minute before we continue with the standing wave. Or can we just a half minute, half minute. Okay, so this is standing wave. Okay, we continue back. What is a standing wave? Standing wave is a fixed in location but oscillates with time. These waves are found on string with both ends fixed, such as in the musical instruments, okay, like a guitar. Okay, when you tie to this one, fixed, and this one is also fixed. So when you pluck the string, so you will have a situation like this. Okay, so on the standing wave, there are three cases. Okay, three cases, right? Should know on a standing wave, we have three cases. Number one, close end. Okay, and number two, open end. And number three, open, close end. Okay, so remember, close end meaning that both ends are closed. So the second case will be open end, meaning that both ends are open. Okay, and the third cases will be open, close end, meaning that one side open, one side close. Okay, these waves are found on string, okay, such as in musical instrument, also in vibrating air column. So musical instrument always number one and number two, case number one and number two, and this one is case number three. So first you look at the situation here. So this is what we call as both end, okay, close end. Okay, this is the wave on a string. A wave on the strings. So you will have a situation like this. Okay, so normally we have a tight end like this, say fixed end, and you will have a string. So this is string. Okay, what happened to the string? So when you pluck the string, so it will occur like this. Okay, it will occur like this situation, meaning that this string will be going ups and down repeatedly. Yeah, repeatedly. Okay, up and down, and we can see a different pattern like the one obtained here. Okay, like part A, and you have figure A, figure B, and also figure C. Okay, this is not just these three, but it will be producing a lot of more harmonics. So this is what we call harmonic. Okay, so look at the first harmonic. See, the first harmonic is called fundamental. Okay, always remember, first harmonic is a fundamental. So maybe in the question, they will ask you, try to find the frequency for the fundamental. So meaning that, or specifically for the first harmonic. Okay, well, in order to understand the standing wave, I need you to okay, we cannot learn these things like a very conventional way. So you need to find, first you need to know how to draw the standing wave, how to draw standing wave. Very good examples. Okay, so for the close end, okay, easy. Okay, first, this is both close end. String, when tied, when been tied, okay, when you try to tie the strings to the close end, okay, every time the string meet the close end, it will produce uh, note point, okay, note point, and here A is the anti-note, while N is the note. Okay, so A is the anti-note point, and N is the note point. So every time you see, you come to the fix, okay, where that should be the end of the string. So every time you have close end, it must be note point. Okay, that is the conditions. Okay, that is the rules. When it comes to the every close end, okay, it must be closed with note point. So N and N. So in this case, the one that have a bigger shape is called anti-note point. A. So for the first harmonic, you will only see one anti-note point. Okay, look at the anti-note point here, 1. For the second harmonic, you will see 2. For the third harmonic, you will see 3. Don't bother about the note point. Just look at the anti-note point. So you will see. So can you predict what is the fourth harmonic? So definitely it will have 4 anti-note points. Okay, it's very good to know, to understand by using drawing first. Okay, this is how you draw a close end. Okay. So I'm telling you, this is the right way to learn a standing wave. Okay, the right way. Maybe I'm using my skills. Okay, to get you to understand how better or to understand well the standing wave. Okay, so we will see a lot afterwards. We will see the equations afterwards. But I want you to get to the to at least when you look at the figure, you know. So this is should be how many harmony. If you don't have five antinote points, then the harmony should be fifth harmony. Okay. How about 10 antinote point? 10 harmony. Can you draw five? Can you draw three? Can you draw a fourth harmony? Obviously, yes, because you will only you must make sure that you will draw four antinote point. Okay, the note point doesn't matter, but antinote you must have four. So meaning that if four, you must include another one like this. Okay, so that should be both close end. So we skip the close end and we go straight away to open end. Okay. So this should be the open end. How to draw an open end? Open end is like this. Okay, if the close end have fixed point, meaning that at the end of close point you must draw node point. Okay, regardless of anti-node berapa banyak pun, tapi dekat hujung mesti lukis node point. Ini for close end. But for open end, it's slightly terbalik dengan close end. Apa yang berlaku? Every time you draw a close end, okay. So every time you draw a open end, so this should be open end. Hujung dia terbuka, open end, hujung dia terbuka. So you must draw anti-node point dekat situ. Oh, dia tulis. You must draw anti-node point. Okay, you must draw how to draw anti-node point. Yes, like that. So this one should be A, this one should be N, and this one should be A. So how many A and A? So you will only see one node point and two anti-node point. So this is actually what? This one. This is fundamental. Or first, also called as first harmony. So what is the first harmony? Okay. How can I know this one is first harmony? Alright. Very well. Tadi kita tengok, kalau dalam close end kita tengok A, anti-node point. So untuk open end, we look here. How many node point? So here, let's look. This is the first harmonic. How many? N, 1. And for the second harmonic, you will see double N. And for the third harmonic, you will see triple N. Because N is the most important thing in the open end. Endpoint. Okay. So there are only three node point over here. Okay. And the middle node is like this. Tempat dia mengucuk tu, tempat dia bertemu tu. So that is node point. Okay. But the open end will have an open part. So this is the A. We don't bother about A because this is open. And we want to know what is the node. And afterwards we know. Okay. So for open end, we need to define, we need to look at the end, at the node pattern, node point lah. Okay, we should calculate node point. Then we know this one is the first harmonic, second harmonic, or third harmonic. Okay, so what to know? Okay, what to know inside the node and anti-node point? Okay, now we go back to the wave on the string. So the wavelength refresh back. The wavelength of the first harmonic is twice the distance between the wall. Okay, twice the distance between the wall. That means when the string is actually L, so when you do a standing wave, they will have 2L. Okay, 2L. So meaning that seolah-olah pergi L, balik pun L. 2L. Okay, 2L. If the speed of wave on the string is V, so it follows the frequency of the first harmonic should be, so V equivalent to lambda 1 F1. So what is lambda? Lambda is 2L. Okay, remember the wavelength for the first harmonic is 2 lambda 2L. Okay, 2L. So you include this one in, and therefore the frequency for the first harmonic is V over 2L. What is V? Speed of sound. What is 2L? 2 times length of the string. Okay. 2 times length of strings. Okay, so that should be the first harmonic frequency because this one is only for fundamental. What if you want to find the frequency for the second harmonic, for the third harmonic? So how to do that, right? So we need to use these equations, right? So the wavelength for the second harmonic is the distance between the wall. The distance between the wall is L. Okay. And therefore, okay, in the end, tengok ujung sekali je. So the F2 is actually 2 times F1. Okay, 2 times F1. And how about F3? And F seterusnya. Okay, so for the conclusion, so so for F3, it should be 3 F1. How to get F1? F1 is V over 2L. Okay, so when you know F1, you can find what is F2, F3, F4, or F100, F1000, still using the same equation. Okay, so in this case, you may find what is F, what is lambda. Okay, this is the most important thing. Not just F1, not just F1, it should be frequency and wavelength. So you need to define because V is already no, because V is the speed of sound. Okay, easy. Right. So like this one. One of the harmonics on the string is 1.3 meters long, so this should be L has a frequency of 15.6 hertz. Okay, frequency. One of the harmonics on the string 1.2 meter has a frequency 15.6. The next higher harmonic is frequency of 23.4. Okay, so the next higher harmonic, meaning that we don't know yet. This one is the F1 or maybe F2 or whatever, but this one is slightly higher. Okay, find the fundamental frequency. So in this case, we can know that 15.6 is actually F2 and 23.4 is actually F3, and they want to know what is F1. Okay, what is F1? So F1, F2 is actually equivalent to 2F1. So F1 ialah F2 divided by 2. Kan? F2 divided by 2 or 15.6 divided by 2 equal to 7.8 hertz. The same. Okay, or you can use 23.4, meaning that F3 minus F2, F3 minus F2, because it should be one frequency higher than F2, so this should be F1. Okay, and the last is fundamental frequency, and B is speed of wave. Okay, speed of wave, right? So F equivalent to V over 2L. You do have F, you do have L, and you need to find what is V. Okay, right. So that should be what we should calculate when we deal with standing wave. So you can see on the guitar, for those who are playing guitar, you should know that every note will have its own frequency. So that should give you a different view afterwards when you play guitar. Okay, where you have C or the C sharp, where you have D. Okay, you need to find what is E, and okay, F, and so on. Okay, so they will have different frequency. That's why we should plug on the same. We should point. We should okay, uh, get our fingers on the right strings to get the notes. Okay, so look at the last time. Okay, the last thing. For the open end, also the same. Okay, lambda is 2L. Okay, lambda is 2L. Lambda 1 is 2L. So F1 is equivalent to V over 2L, F1. And for F2, again, 2 times F1. F3, 3 times F1. Okay, so just use the same concept as the one we did on close end. Okay, now we look at the last part. Okay, the last part, okay, this one is very special. So you need to look carefully. You need to understand well, really, really careful. Okay, so this one is called open close end. Okay, open close end. By the look at the names of the open close end, meaning that one part of it is the open and one part is closed. Okay, but try to understand when we have open end. So how can we draw the pattern? The pattern should be antinote. At the close end, the pattern should be note point. So that is something you should understand first. How to draw the pattern. Then we go straight away to the situations. Okay, this not the same as open end and close end. At close end, we know every time at the fixed end we should have note point. Every time kalau untuk open end, every time you add the open part, so you will have to draw empty note point. But this one contains both open and close together. So how to write down? Okay, this one. Okay, in the open and in the open end and close end. Okay, the number of frequency starts from first, second, third, and so on. Sama, dua-dua pun sama. Okay, untuk open end and close end pun sama. Meaning that end starts from N1, 1, 2, 3, and so on. Okay, maksudnya dia tidak ada gap. But for the open close end, okay, open close end, slightly different. Okay, so how to determine the open close end? Okay, so the first harmonic. Okay, look at the first harmonic. The first harmonic is like this. Okay, at the open part, this is open part. Open, you will have to draw an anti-note point, while at the close end, you will need to draw a note point. So ada note, ada anti-note. Tadi kita tengok dekat close, kita tengok jumlah anti-note. Dekat open, kita tengok jumlah note. Yang ni nak tengok apa? So you need to understand that the pattern here is for first harmonic, or should we call fundamental? First harmonic or fundamental. Okay, itu je. Dia memang tak ada bayangan macam mana, tapi just for your own thoughts only. Okay, this is not the real theory or what. For my understanding, I'm just using this one. Okay, just look at the figure B. Look at the figure B. So you will see some sort like ikan punya type lah, ikan punya bentuk. So actually apa yang what did I do is I just bahagikan benda ni. Bahagikan dia. Apa maksudnya? Okey, cuba bayangkan, cuba tengok part di bawah ni. Sama kan dengan part yang sebelah ni? So right now we have one part, we have two parts, and we have three parts. So that's why this one is n equals to 3. Okay, this one n equals to 1. And try to do on the figure C. Okay, belah. So you have one part, two parts, three parts, four parts, and five parts. Okay, so this is n equals to 5. Hey, what happened to n equals to 2? N equals to 4. Mana pergi dia? Okay, so sebenarnya for the open close n, the n is actually like this. Okay, n is not a even number. It's just odd number. 1, 3, 5, 7, 9, 11, 13. If you meet one that saying that open close n have n equals to 4, then it's bluffing. Okay, because for the standing wave, the open close n will only have 1, 3, 5, 7, 9, and so on. Just odd number. Just odd number. And the difference also at the lambda. Lambda is not 2L. Lambda is 4L. Okay, for the open close n, lambda is 4L. So when you have V equals to F lambda, so F is V over lambda, so V over 4L. So F1 is V over 4L. How about F3? Because it doesn't have F2, so straight away 3V over 4 lambda. Okay, or should we call that F3 is actually 3 F1. F5 is actually 5 F1. The same goes to the part. Okay, but you need to know the drawing, the lambda, and the frequency. Okay, so we have time to look at one example. So let's look at one example. An empty soda pop bottle is to be used as a musical instrument in a band. In order to be tuned properly, the fundamental frequency. Look at the word used. The fundamental frequency. This one should be F1. Must be 440 Hz. If the bottle is 26 meters tall, okay, 26 meters tall, centimeters tall, sorry. How high should it be filled with water to produce the desired frequency? Remember, this is the air column. Air column means we need to, every time, so this one should be open, this one should be closed. So we don't know how many frequency that we will be fitting into this hole. Okay, kita tak tahu ada berapa banyak node point, anti-node point, we doesn't know, but we only know frequency fundamental is 440. Okay, how high should be filled? So we need to define L. Alright, so in this case, V equals to 4L, L is equivalent to, remember, F equals to V over 4L. Now we bring L to atas over for F1. So the L is 0.195. Okay, 0.195. Okay, the bottle is 26. 26 centimeters. So the minus with 19.5, so we will get 6.5. So you should fill up, okay, only 6.5, okay, 6.5. It should be filled with water about 6.5. And part B, what is the frequency of the next higher harmonic for this water? So this is F1, and we need to calculate F3. F3 is 3F1. Very easy. 1320 hertz. Okay, very straightforward. Okay, you just need to understand the drawing, okay, the conditions, antinote or node, okay, and of course you should know two things, just lambda and frequency. Okay, I think that should be the end of our discussion in terms of wave and sound.